All right, Prop 21 is somewhat wordy. It says, if on one side of a triangle, from its extremities, there be constructed two straight lines meeting within the triangle, the straight lines so constructed will be less than the remaining two sides of the triangle, but will contain a greater angle. So let's see here. I kind of have this little setup here just to kind of try to rewrite this in maybe slightly clearer language. So the idea is, suppose that we have two lines, BD and DC, and we can connect them in such a way that the point D lies inside triangle ABC. So it might look something like this. So here are our two lines, and here's our point. We'll call it D. So we have these two lines that can be constructed in such a way that the point D, their intersection point, but really both of the lines themselves, lie within triangle ABC. Then Euclid makes two claims for this situation. Claim one, he says that BA, or I'll say AB plus AC, is greater than DB plus DC. So that's the first claim, is that the sum of the outer lines, AB plus AC, is going to be a greater sum than the sum of DB plus DC. That's the first claim. But then the second claim is that this internal angle, BDC, is greater than the angle BAC. So angle BDC is larger than angle BAC. So the sum of the legs of the triangle, of the inner triangle, are smaller, but the angle of the inner triangle is larger. All right, and I think that this is kind of an interesting one. It's sort of tough. Yeah, maybe if you'd like, just take half a second and sort of pause the video and see if you can kind of come up with a proof on your own, because this is one that I look at it immediately and I go, oh my goodness, that seems kind of intimidating. But of course, Euclid is much more clever than I am. Of course, Euclid may or may not have really actually written many of these. Most of these propositions Euclid did not write or prove himself. Euclid probably was just very good at compiling. That's kind of how I view it. Rather than him being this incredible mathematical mind, he was an incredible mathematical mind, but not in the sense that he was making these crazy proofs. He was an incredible mathematical mind because he could take all of these pieces that had probably been, the Greeks had been compiling these propositions for centuries. He took all of them and he was able to rearrange them in such a way that they build on each other. So that's really kind of Euclid's genius. In any case, who knows who actually wrote this proposition and proved this one. But let's go through and prove it. All right, so step one is we're going to extend BD to a point E, such that E is the intersection of BD with AC. So I'll say extend BD and let E be the intersection of BD with AC. Step one. And when we do this, so it's over here. Here's E. When we do this, notice we just created a couple of triangles, 3 different triangles on the inside of triangle ABC. And that will be really useful for us. All right, so what can we say now that we've created these 3 triangles? All right, well, first of all, we can say that if we look at triangle ABE, so like this top triangle, the top triangle that we created, in triangle ABE, we know that side AB plus side AE is greater than side BE. And that comes from proposition 20, which says that, which was the triangle inequality. The sum of two sides of a triangle are greater than the remaining side. All right, so what does Euclid do next? Well, his next line is let EC be added to each. So EC is what we're going to add to each. So from this we get that AB plus AE plus EC is greater than BE plus EC. And Euclid doesn't actually write out this step because he just jumps straight to saying let EC be added to each side, and then he says, therefore, BA plus AC or BAAC are greater than BEEC. So where does he get this BAAC from? Well, AB is BA, but notice that AC is equal to AE plus EC. So this right here, AE plus EC, that is AC. So more concisely, we have that AB plus AC is greater than BE plus EC. So BE plus EC, which is close to what we want to prove. We want to prove that AB plus AC is greater than BD plus DC. So how do we get that? Well, we kind of just iterate this same logic, but using a different triangle. So if we look at triangle CED, which is this rightmost triangle over here, CED, we again get that, and we need to be careful about the sides that we use. We get that CE plus ED is greater than CD. So CE and ED is greater than CD. And again, he says, what are we adding to each side? We're adding DB this time. So let DB be added to each side. Well, then we would have CE plus ED, at least on the left-hand side of this inequality, we would have CE plus ED plus DB, but ED plus DB is BE. So we end up with the inequality that CE plus EB is greater than CD plus DB. Just going to try to focus this again. It somehow looks a little bit out of focus. I can't really tell. Maybe it's just my eyes. Maybe I need glasses. All right, what's next? Okay. All right. And he says, but BAAC were proved greater than BE and EC. So, right. So if you look at the right-hand side of this inequality and the left-hand side of this inequality, we have matching pieces. EC, well, I wrote it differently, but EC is the same as CE. BE is the same as EB. So we get this chain of inequalities, and I'll just kind of write it out. We get that AB plus AC is greater than BE plus EC, but we also have that that is greater than CD plus DB. And that was what we needed. That was one of the claims, right? So, right here's the claim right here. AB plus AC is greater than DB plus DC. So we've proven that part. This is a B. It doesn't really look like it on the camera. It's a B. Okay. All right, so we've proven the first claim. Now we need to prove the second piece, that this internal angle is greater than the top apex angle. All right. So if we look at, I'll say next, in triangle, what triangle we're looking at? We're looking at CDE. All right, so CDE, again, this right-hand triangle right here. In CDE, we know that the angle BDC. So BDC is this angle right here. And this angle, BDC, is an exterior angle to CDE, which means that this angle is greater than the interior and opposite angles. Specifically, I believe we're going to say it's larger than this angle E right here. Yeah. So in CDE, we have that angle BDC is greater than angle CED. And that comes from proposition, which one was that, 19? 16. Yeah, 16, proposition 16. The exterior angle is larger than the interior and opposite angles. So BDC is larger than CED. Can you see where it's going now? Is we're going to make another comparison. So if we look at in triangle ABE, then this angle that we just looked at, angle CED, is exterior, which means that it's larger than the interior and opposite angles. So in triangle ABE, we have that angle CEB is greater than angle BAC. All right. So, and this is really like the chain of inequalities that we need, although it might not totally look like it, because in this first inequality, we're talking about angle CED. In this second one, we're talking about angle CEB. They're the same angle. So we could say since angle CED equals angle CEB, we have, what do we have? Here's our chain. Angle BDC is greater than angle CED, which is equal to angle CEB, which is greater than angle BAC. Which is the second thing that we needed to prove. So, there it is. Very clever stuff. I can't fit it all on one screen, but yep, there it is. QED, therefore, etc.